Yeah, the stage is yours.
Are you there, Sergey? Are you ready?
Yeah, I'm sorry, you're ready.
Whoa, Fernanda, that's a long title.
Yeah.
It's a paper cut.
Well, hi everyone. We're going to present this beautiful paper with such a long name. The content of this paper, wait. You're seeing my computer, right? My screen. Okay. The content of this paper, it's super essential, but very basic. So for the dynamics of working with distributed systems. So please put a lot of attention. This is about time clocks and the ordering of events, of course, for distributed system. And don't be scared. It's actually a pretty simple topic. And even the exercise are kind of fun to solve. I think it's just an irrational fear for long mathematical formulas, but understand them, it's easy. So don't worry, we try to summarize everything to be easy to digest. There is a conventional definition for what a distributed system is. So it's good to have it in mind all the time. Distributed system involves multiple networks of computers which communicate each other by passing messages among each other. Well, but how those machines know the moment or the time in which the messages were sent? That's actually the challenge here. You know, because later we can use this time for organize those messages or to show them. So it's essential to know where those events happens, but that's the point. It's very different to see the time as a number, that rather than a moment in all the time that happens. But we're going to talk about that later. And the main question here is how we order events in time. Well, in 1978, a computer scientist named Leslie Lamport tackled this problem by his main seminal, or well, this paper called Time, Clocks, and the Ordering of Events in a Distributed System, which is precisely the paper we try to summarize. And even when it's in a short, well, how can I say that? Even when his paper is pretty short in number of pages, it's very dense in concepts, and it's still very relevant today because autonomous computers communicate following Lamport's protocols. So it's a topic that is still very relevant today. He has a long career. He's currently 79 years old. So yes, he's still alive. He's not dead. He has lots of nominations, prizes, and contributions to these areas of distributed systems. And well, because of his career, he loves to write scientific papers, biographies, etc. Lots of different kind of writing purposes. And because he loves to write, probably you heard about LaTeX. This document preparation system. It's like a language for giving style to documents. Well, giving this stylish look to documents, but it's pretty beautiful. It's pretty cool if you heard about that. Lamport was the first, how can I say, the first developer of these languages for creating these documents. So it's pretty cool if you want to look at them. But let's begin with the actual concepts of the paper he wrote. And there is this. So please, we try to divide the paper in three main topics, and the concept of partial order, the logical clocks, and the algorithm, well, Lamport's algorithm. So let's start with the partial ordering concept. Lamport first introduced this concept, but we'll try to explain pretty easy because it's easy. Just remember this theory. Let's say we know for sure that A and B are events in a lineal process. If A and B causally affect each other, then we use an arrow to represent that. And we said A happens before B. That's all. That's causal order. It's pretty simple. But well, this might be how can I say that? Like, this might be true if it satisfies the three follow cases. The first one, the case one, if A and B happens in the same process, we say that A happens before B. It's, well, you cannot receive a message if you don't send it, right? The second case is if A send a message to B that is in another process, you will notice that there will still be a causal order, because you will see this arrow crossing between them in an exercise, for example. And in the last case, the third case, it's very logical. If you see that A happens before B and B happens before C, then you can say, well, A is before C. It's called this property that it's transitive. And basically, those are the three main cases of this causal ordering concept. But there's another, the opposite thing of causal order, that is concurrent order. Let's say we don't know what event happened before that. We know that A and B cannot how can I say that? We cannot say that A and B causally affect each other because you are not seeing this arrow that are connecting them, and they are in different processes. We call this, well, we say that A and B are concurrent, and we represent that with an arrow with a cross in the middle of the arrow. And for partial ordering, that's only the concepts. Well, that's the only concept that you have to remember. There are just concepts. You remember the main cases, and my partner will explain you what logical clocks are. So I'm going to change my view to my partner so he can control the presentation. Okay.
Thank you. Can you see my screen now?
Yes.
Yeah.
Yes.
Okay, thank you. So now let's talk about the logical clocks. So when we are talking about time and when we are talking about distributed systems, we cannot use a global clock because that's not easy to achieve because of the different locations and all the different problems that we could have when targeting a global clock. And the same happens with a physical clock because a physical clock is attached to a physical object. And because we are talking about something that could be in different physics places, that's why we cannot talk about that. So then we can talk about like the logical clocks, and that's something that Lapper introduced. So when we think about time as a person, our approach, it's more about the time when we have something between, like, let's say 3:15 to 3:16. It's how many times do the clock clicks between those two different times. So that's how we think about time. But then we have the other approach that it's more about like, what is the order of the events that happen before something else. So we have an event happening that it's sending a message, and then we have the other one that is receiving a message. So that's a different approach that we need to think about. And it's not about just the regular time that we use when we think about like our day-to-day activities, but more about like the order of the events that we have. And as you can see here, we have this formula that it's how we can explain that order in a proper way. So given two events, in this scenario, we have event A and event B. One is caused by the other. In this scenario, it's A causing B. Then the timestamp of the caused by is less than the other event. It's saying that the time from event A, it's the timestamp it's going to be sent from event A to the event B. And this could be really confusing if you look just at the formula, but it's going to be really clear once we start with some examples. So once we have that in mind, we start with the algorithm. So Lamport introduced a way to define what is going to be the order of the events in an easy way. And as I mentioned, when we have different events, we are going to send the timestamp at the same time that we are going to, it is attached to the message that we are sending, right? But how we can calculate in a proper way which event are it's first and which event is after something else. And the problem is that when we have a linear time that it's in just one node and it says node, it's a process. So if we have one process or one node, it's really easy to do that because you are going to see just like the order of the events. But once we introduce like different process or different nodes, we are going to have the problem of which happened after which one, because we have concurrent events. And what Lamport was proposing is that every time we are sending a message, we are sending the timestamp. And we have a specific timestamp when we start each of the nodes or each of the process. So we compare between the, for this event, what is the value that we have for that specific process, and what is the value that we are getting from the other event that it's sending with the timestamp. And then we add an arbitrary amount. In this scenario, we are going to say that we are just adding one value. So with that formula, we can determine what is the value of each of the events that we have, and we can arrange all the different events that we have. Again, this sounds complicated if we just look at the formula, but let's think about this scenario. And I want to introduce an example that is something that we can see in our day-to-day. So sometimes we use websites like Expedia or booking.com that it's exactly what is happening here. We have the user that we could be the user or mom or the one that it's buying a ticket. And then we have like Expedia or Airbnb or Booking. And then we have the other layer, and let's call it like Aeromexico or Volaris or any airline in the world. So we have three different systems that are working together in order to achieve the goal that it's booking a ticket. So we will have these three different nodes, three different processes, and each process is going to communicate between the other process. And as you can see in this example, we have some events that are sending from one process to the other, and that's going to be really clear to follow because we can understand the order by just following with the eyes like the arrows. But then we have the problem. So for example, here in the second process in the Expedia layer, we have the process D. And that's concurrent with the other events, like for example, F. So that's when we introduce the algorithm and the formula that we were looking at. So if you can see here, each of the nodes, they start with 0. So then we have the first event for each of the nodes. So if we follow the formula, we are not getting any timestamp. We are not getting any value because it's the first event. So then we just add 1 to each of that's the formula that we are using here. And then we will see that we have the value of 1. But then what happened with the second process with Expedia? We are actually having a message sent through that process from the first process from the user. Let's say that the user is typing like the place that he wants to visit and the date. So we are not starting from 0 on that specific, because we are getting the timestamp from the first event on the process of the user. So if we use the formula, we are attaching the value of that specific event. So as you can see there, we have the value of 2. And we will continue with that in a way that first we try to understand what is the process value, and then if they are getting a message, if they are getting a timestamp from the other values, we will add those values using the formula in a way that we can handle that. So then we will have something like this, that it's more clear, it's more easy to read. We will have the user that is trying to buy a ticket, the Expedia node, and then the Aeromexico node. And as you can see here, it's more easy to read because we already have the values that they have. But then we have this problem. What happened in case of a tie? And that's when we use the priority of the different nodes that we have. And it's when Lamport introduced the Lamport total order. So what he said is, like, in case of a tie that whichever process has a lower process ID, it's going to be the winner. So here we have the 2 different ways that you will see it, and it will vary depending on the source. But following the rule, as you can see here on the Lamport total order, in case of a tie, whichever process has a lower process ID, it's going to be the winner. So depending on the value that you assign, it's going to be the order. And then you will be able to see, like, let's say, like, we can have A, B, E, C, D, F, H, D, G, and you can continue. And that's how he solved this problem. And if you try to figure out this with another approach, it's going to be really complicated. But once you start using this, and once you start thinking about all different scenarios where we have these 3 different nodes working together, you will start to realize that it's something that is very common, and also not just like in the technological world, but it could happen also when we are ordering food in a restaurant. It's the same. So if you want to think about that, just think about the regular scenarios that you have and how we are solving that.
Sorry. Well, the problem at the end, or as a way to make a summary of this, initially computer scientists had no idea how to deal with communication delays. And in that moment, Lamport was reading about timestamps to determine the total ordering in databases. Actually, to avoid casualties in the same manner we're trying to do with distributed systems. And by introduce the concepts of Lamport or total ordering and well, all these formulas that he put in his paper, Lamport totally changed the game. And now scientists often use these formulas of event order to prove system correctness. Basically with this, we avoid things that, can you change to another? We avoid these kind of problems. The computer can crash, and well, if we don't order the messages we are sending, probably they're not going to be delivered. Probably we doesn't have any kind of chat, any kind of social media, or even video games. So thanks for this. Can you change the slide, please? Hello? Ah, I don't see my screen. I don't know what happened. Sorry. Okay, thanks, Paul. For everything and more, thank you, Lamport, for introducing all these concepts. And if you have any problem understanding the example, we can do it together by writing in the screen so everyone can understand this. So basically that would be all. And thank you.
Okay, thank you guys. The floor is open for question and answer.
I have a question.
Go
For
ahead.
the Lamport algorithm, the C, could you explain me again, Fedor or Sergey, like how do you use that formula?
Sure.
Thank you.
Yeah, let me share my screen.
You can write on top on the screen actually with the pen.
Okay, thank you.
If it's easier.
So we have, this is the formula, right? This is the one that you are asking
Yes.
about.
Right.
Okay, so let's say that we have an event. And on that event, we are going to send. So in order to understand better this one, we will need to go back to this one. Do you understand this one?
Yes, I understand that the timestamp from event A happened before B.
Okay.
So it's smaller. Right?
So let's say that we have this formula, and here we want to know the order. And because we have this, we know the order, right? So we know that we are sending something on the event A to the event B, right? So let's say that this is the first event. This is when I get to the website. I'm the user, right? So on the note, on the process of booking the ticket from my side, from the user side, this is the first step, right? So this one has the value of 1.
Okay.
Because if we use this formula, let me go to the next one. Okay. So here, what we have is this. Let me just clear this one. We have, let me see which one is the one that I was using. I think it's this one.
Oh, I can do it also. Sorry.
Okay, yeah, sorry. Okay, so the formula says that between 2 different values, you are going to select the maximum value. So let's say that for the first step that I'm getting to the website, the first event, it's going to be for me selecting which are the places and the dates which is the place and the date where I'm going to travel. So that's the first step. And because it's the first step, for the event 1, that it's the event that I have, the value is going to be 1.
Okay.
But because I'm not getting another, so this is not getting from another event, we don't have any other value here, right? So this value is going to be 0. Or, sorry. This one is going to be 0 because it's the first event. And we are not getting anything. We are not receiving anything. So the value is 0. So between those two numbers, the only value that we have is 0. So the only thing that we have to do is to add one value. So then the value for the first task is going to be 1. And now let me move to the next slide to explain in a better way. We have this one, that the value here is 0, the value here is 0, and the value here is 0, right? So I was talking about this one. So the first value is 0, and we are not getting anything here. So the only thing that we could do for the formula is adding +1. So then the value for A is going to be 1. Is that clear?
Yes.
Okay. And then if we continue with the actual flow that we have here, we continue with C, right?
Mm-hmm.
Because what we have here is once I type on Expedia and I click search, Expedia is going to look at the API and look for the dates and the place, right? So what we have here, it's 2 different values. First is the value that we are getting for the node, that it's 0, because we have 0 here, it's the first event. And then we are attaching the timestamp of the value of this event here. So this event, the value it's 1. So we are attaching that value here. And the formula says, from these 2 values, which one is the maximum value? It's 1. So once we have 1, we added another 1, and the value is going to get 2.
Okay.
And then let's say that once Expedia got that information on the API, they are going to bring that to the front end so that they can display the information. So here, we start from the previous timestamp. That's the one that we are having here, right? So the value it's already 2. And we are sending the value that we have here, that it's 1. This one has the timestamp that is 1.
I got lost there. How do you get the 1? The timestamp from where? From B.
Mhm.
Yeah.
Okay.
So we have 2 different values here. We have this value, that is the value from C, and the value from D.
Mm-hmm.
And then from these 2, we got the winner, that it's 2, and then it's +1 because we add 1 value. And we got to the value of 3.
Actually, the 1 comes from the B. I think that.
From the B.
Oh, sorry. Yeah, I was not looking at. Yeah, thank you for clarifying that. Yeah, sorry, I was not looking
And
at that value. Yeah,
B gets his value in the same way A gets
Yeah.
the value of 1.
And
yeah,
actually,
sorry.
I have a doubt there. Is the possibility that we can have 2 events launching the same event?
No, sorry, it was my mistake.
No.
So-
I am also asking another question. Is the possibility that we can have 1 event caused by 2 different events, or more than 2 events? I mean,
Trying to follow what Lamport said before, yes, but in case of a tie, even when there are different processes and or the third event is calling 2 events, those events also have their own ID or their own internal
No.
clock.
actually, my question is, for example, in this case, D is caused by C, or B is caused by B. What happens if, for example, also E is caused on D? Is that a possibility?
Well, technically, it's possible that you can have that one triggers two events, but if we follow the rule, is that
Can I comment on that?
we use the other formula.
Yeah.
Can I go
Sure.
ahead? I mean, what something is happening here, don't get confused. I mean, how can I say it? It's, for example, you were saying, I mean, D happening before B, okay? See, what if there is like a E happen also before D? I mean, we are talking about like each event. So if that's also the case, then you're gonna see two different events.
Yeah.
It's not, for example, a function that getting updated like by two different inputs. Don't confuse that. This is, each one of these are just one event. You know, if for example, D is getting, for example, B updating D, then E updating D, those would be basically two different basic events.
Okay.
You know, at the end, for example, that's not going to happen exactly the same time. You know, because you're ordering at the end, you're ordering different events.
Yeah, but the formula is just calling two previous events. So the formula can be for whatever number of events that you want.
Yeah.
Okay, got it.
Sorry.
No, it's okay. Continuing with my question, now that, okay, I understood how the event D is number 3. So the first event, the first, let's say the first timestamp from the formula E1, that value is retrieved from the previous event, right?
Mhm.
And the second event is retrieved from the formula. No, sorry, I got super confused.
You mean this one or?
Okay, no, maybe my question now is, now that you have how do you order these events? Let's say that I can see that C has the value of 2 and E has the value of 2.
Oh, yeah, I know where you're getting. Now that you have the different values, how do you order those, right? So that's when we move to this approach, when it's more clear with the values that you have. So you have the different process and you have the different values. And with that, it's going to be more clear for you to look at the actual data, because here it's really confusing, and you will try to figure out by just following the values and the arrows, but it's going to get you confused. But if you follow this step where you actually look with the different values and the different process, it's going to be more clear for you what is happening there.
Okay, yeah. Actually, yes, it is more clear. So E, C, and F are a tie, right?
Mhm.
Yeah,
A,
here.
E is one
And then-
tie, E, C, and F, there's another tie.
Another tie, okay.
And the way Lamport said that, how can you deal with these kind of ties? Well, you determine, how can I write this? Let's say that process 3 is your lowest one. So you put the B1, the B before A.
Okay.
And so on. Let's begin with the second one. Okay, your lowest one it's F. So then it follows F, it follows C, it follows E. That's how do you deal with those ties in time.
Okay, thank you.
Okay.
I don't know if someone else has another question, but can I just, sorry, quickly, can you keep doing the formula for the, like, go back to the other slide and do one more formula for another event? Let's say.
Sure.
Event.
Which one do you want to do?
We were at the event D. Let's go to another one, to the next event from D, and for example, L.
L. Okay. So remember that we have the value of D, right? And then we have, is this L? Oh, yeah, it's L. Okay, so
Sorry, no, let's do H because I can see that L has also the K is causing L. I want H that no one is causing H.
Actually,
okay.
you can see it like this way. Okay.
Actually, E is causing H.
Mhm.
E is causing H?
Yep.
You remember the causal order? Each
Mhm.
process 1, process 2, process 3, this big arrow, let's say A causes E, E causes H, H causes G, that way. So if you don't see any arrow crossing between processes, you can see E causes H. So the value in E is going to be one of the in your formula. Sorry.
Okay.
Yeah, so you remember that I was confused with this one because I was
Mhm.
thinking that I was getting this value from this, and I was not looking at this arrow. And it's
Okay.
because, yeah, each of these is an arrow. Because to not get confused, we don't draw those arrows because it's what
Like
we
that.
already explained.
Okay,
Yeah.
yeah. Thank you. Yeah, next. We can move on.
Okay.
Okay. I have a question about this, and is what about if there is redundancy in one of the process?
But it's not about process, it's an event. So you do like,
Yeah, but what about if one of the process, for example, N is causing redundancy, and then N is going to cause launch again the event H.
but it's not going to launch again event A. It's going to launch event whatever we want to call next.
Yeah,
So
what I am asking is if that is a possibility.
In theory, this whole algorithm it's to avoid.
Yeah. Pedro has hard questions.
Yeah.
I mean, if you're meaning, for example, sorry, I interrupted. If you're meaning by, like, for example, you have two different event N on process 1, that's what you mean?
No, what I am asking is, for example, what about if for some reason I have a condition in N, the event N, if something happens in event N, then I want to start again with event E.
Oh, with event L, you mean?
E.
So
Okay.
I can
Okay.
help, I think.
We're going to talk about today a little bit about that, but if you want to add something, Paul, but so short, okay? But I'm going to talk about the basically snapshots and consistent code, how you make sure things works basically. But Paul, go ahead.
Yeah, I was going to say something like that, that is like a snapshot.
Yeah.
The things on the numbers are not like functions that are being called. It's like timestamps. So E represents a timestamp during the day, let's say. So it's not like N can call E, because E, it's the timestamp or the time where that event, well, where something happened. So we call an event when something happened. We don't call an event like a signal, like in programming languages. So on this concept, using a event as a, we are using events as timestamp, let's say.
Okay. Got it.
Thank you, Paul. More questions?
Yes, one quick question. The formula from Lamport algorithms, it says that an increment by an arbitrary amount will be performed. Will this increment be fixed always? I mean, if you choose 100, 1000, something different to one, this value will be static or fixed? Or it should be always 1?
Oh, I understand. Most of the examples you will see a 1, but you can determine your own arbitrary argument.
Okay.
Like it's like a tick-tock in a clock, in a physical clock. You can say, well, 60 clicks, it's 1 minute, and that kind of.
Okay. Thank you.
Okay, and other question, can we see the formula for breaking the tie?
For what, sorry?
For breaking the tie.
Ah, for breaking the tie. Okay.
Yeah, that one. No, that is not that one. Because I think it is supposed that it should be something like the process, we add the, I mean, to the clock, we add the number of the process, and the minor one is the one that happens before, right?
I think
Right.
it's the question of the two examples. Do you remember, Sergey?
No, I am in the tie. Yeah, there is a formula, right? For breaking a tie or a condition, I think, but we don't have it here.
Yeah, here it's in case of die, that whichever process has a lower process ID, it's going to be the winner.
A lower process ID. What do you mean by a lower process ID?
Yeah, what do you mean?
My assumption is that
in this case, 1 is the is lower than 3, right?
We saw this example in, well, as Lamport said, you can determine that your process 1 is your highest or your lowest, depending of the program you are writing.
Oh, okay, got it.
We saw some examples that people took the process 1 as the lowest and others who took the process P as the lowest, but you have to determine that. But it would be incredible if teacher, you can determine like this is going to be the
standard.
The standard.
Yeah, because we saw those.
Again, it's like the question that Hector asked about the jump in the clock. Like, I mean, you can consider any arbitrary number. It doesn't really matter. You consider that 2, still you're gonna order all the events the same. It doesn't really matter. You consider that million, still your increment gonna be million. I mean, it's the same. And for the lower process, again, it's how you define it. If, for example, let's say you are assigning to this server A process number A, like 1, 2, 3, 4, then you say, okay, that's my ordering. That's how I want to order it. So process like 1, like in this example that they are showing, 1 gets higher priority than 2, 2 gets higher than 3, or you want to do it the other way around, it's perfectly fine. It's just basically an agreement in your distributed system, how you want to order all the events. Remember, all they're talking about is about totally ordering all the events in different processors. Processors, I'm not talking about like one computer, different processors, different process happening in different computers.
So actually you can determine which one to pick. If my process 1 is the lowest ID one, it's going to be like this way. And if you determine the process 3 is the lowest, it's gonna be like this way. Oh, okay. So yeah, it depends.
Yeah.
And you can choose which ID it's going to be the lowest in your program, apparently.
Question? More questions?
Yeah, I have a question. Can you go back to the previous slide, please?
They are killing you guys. But it's
Sorry.
fine.
That's fine.
That's the idea.
The slide with the arrows and in the events.
This one?
That one, yeah. So there you are saying that event E is calling, is triggering, let's say, event I, right? In the process 1, event E. Yeah, that one is triggering event I, right?
Yeah.
Okay, so you are saying that, well, Lamport said that you have to take the maximum counter of that process and then send it. And the logical clock will be the sum of those, right? Then why is 4 in process, in event I?
Because you are taking E and G. 2 of E and 3 of G. So which one of these is the maximum value? It's 3. and 3 plus 1, wait, sorry, it's 4.
Okay, so you just take the maximum and you not add up the values, right? You just take the maximum value and okay.
You're not
And
zooming.
increase the counter, okay.
That's what max mean. Yeah, max and the values inside of the, I don't know what of those are called in English, but
Parentheses.
Nice. Brackets.
You are taking the maximum one, the highest one, 3, and you're summing your
Okay.
arbitrary value. That's all.
Yeah, okay, thank you. I thought that you have to add them up, but no, you just have to take the maximum. Okay, thank you.
You're welcome.
More questions? It's fine. Feel free to ask. I mean, it's really good that Luis, Pedro, and Charlie are here, because basically what they did now, Fernanda and Sergey, is they covered the second week of the class, which was basically the first week was general network communication. Second week was the important one that you needed to know, and I'm really glad that you saw that. That's why I guess more questions come from Luis and Pedro. So no more questions?
I have one question, but it's not related with the topic. It's
okay.
What program are you using for the presentation?
For making it?
Yes. Is it PowerPoint? I mean, it isn't right.
No, I did it in Illustrator.
Oh, okay, just that looks nice.
But you can do it also in
I have a question. Did you draw Lampert's picture yourself?
This one?
Did you draw that picture yourself? In the second slide, you show his picture. Out of topic, sorry. Yeah, this one.
I know how to illustrate, but I didn't have the time to do that, but I found it.
That's because it suits a lot your style. That's why I thought you did it. So, awesome. Okay.
It's not mine, but I wish I could draw like that.
Okay, nice. Any unrelated questions anyone has? Okay, thank you guys. We're not done yet. Remember what we were doing. So I'm going to share the screen. You remember after we do the presentation, then we do this. Do you see my screen?
Yes.
This is what you see, or you see another screen? I have a lot. You see
We
my.
are looking at the presentation.
Okay, perfect. So I have another thing for you, just to remember, if you see my head is changing from here up to here, they're all my screens. So I'm looking at different things like your face, like the slides here, then my notes and the slides here. So that's why my head moves a lot here and there. You remember we were doing these things after each presentation?
Yeah.
So I'm going to do the same to be fair. So the first lucky student is that was close. Ricardo Arturo. You're here? No? Yeah. Yeah, Ricardo, you just came. So I want you to tell what was the problem being solved, Ricardo Benitez.
The problem being solved is to determine the way the things,
We are hearing you very hardly. Now we don't even hear you. It happens, be patient. So you prepare yourself for these other students, other questions. The key insight, main technique, how to paper advance the state of the art. Okay, go ahead, Ricardo. No?
think he's talking, but we cannot hear
Yeah,
him.
we cannot hear. It's fine. If there is problem, we can go to the
Can I
next.
volunteer?
Huh? Any
Could I
volunteer?
volunteer?
Okay, go ahead. Sure.
As a tribute.
Ricardo, we don't hear you. Try to fix it. It's fine. If you have problem, just be here. It's okay. Go ahead, Juan.
Yes, the problem being solved with this paper is to, like, very basic, order the total of events in distributed systems. And how? Well, with the Lampert's algorithm.
Perfect. Yeah, thank you. That's it. That's the idea.
Thank you, Ferenc Sergey.
Sure. Okay, so Roberto Julio Saldaña Hernandez. You're here?
Yep.
Okay.
I am here.
Yeah, okay. So the key insight of the
Key insights, I think, well, the problem is just being set. The solving of the problems of how to handle different events in different, in distributed systems, which is, in different time zones and different concurrency. With the Lamport algorithm, which is, giving a value to the different events and ordering them in a timeline. So it makes sense. And, solving ties, it's part of the algorithm. And I think that's it. Well, different processes. And,
Thank you, Roberto. Yeah, that's almost the key insight is same thing. Maybe I would mention something about the clock when we were talking about itself. So in order to order everything, you don't necessarily need to have precise clock, right? That was the idea we were talking about. So in order to, when we're talking about distributed system, then the ordering of event is it's very important for us. Even if we don't have the precise clock, and we were discussing why it's so hard to have like synchronize all the clocks on all these distributed systems. So it's just fine. You can have this system like to know which events happening before which events. So Javier, coming in.
Yes. Can you hear me?
Yeah.
Okay.
So can you tell us about main technique?
Well, the main technique is to get the nodes in order to see which event occurred first. So we use a formula they used, in which the they add one from the previous node, well, the maximum previous node. So if two processes lead to one node, they add one from the process that has a bigger number. So in that way you can get like a map of which events occurred first. And also you can label nodes according to priorities, or, well, it depends on how you label the nodes, and it shows which one, if it ties with another node, you can order them according to how you label them.
Correct. Thank you, Javier. I'm not going to go to the next one. They already mentioned it's. The other thing also they mentioned. Okay, just to save time, we skip that. But anyway, that you remember the paper was from 1978, 85.
Sorry, I have another question, Mati.
Okay, Juan Pablo. Just I'm going to give you like 5 minutes break. Okay, so we're gonna come back and continue like 7:45. But I'm here to answer your questions. But I'm not going to continue with the course till 5 minutes for the break.
Right.
So, yeah, go ahead, Juan.
Great, thank you. Just like, can you numbered the reasons why no physical clocks are reliable? Is it, I understood it from the previous class that because they get, when time they can oh my god, they can desynchronizate. I don't know how to say it.
They get out of synchronization, right? Mhm.
And are there any more reasons why not physical clocks?
Reason what? I didn't get.
Sorry. Are there any more reasons why no physical clocks? Why physical clocks are not a good system for synchronized?
Okay, I want to like emphasize, it's not that we don't rely on the clocks. I mean, of
Okay.
course, that's important, but it's not what we are doing. We're saying I mean, the clock drifts. You remember we were talking about how to say the quartz. They can get they are sensitive to the pressure, temperature, movement. So the clocks are mostly relies on quartz. I mean, if you are not talking about atomic clocks that are very precise, the normal clocks, and they can drift by the time because they are sensitive to different things like temperature, like pressure. Okay, so the idea, and then we're talking about the preciseness. Remember here again, we're talking about like microsecond, like nanosecond preciseness, not like my clock in my smartwatch with the clock in my like laptop with clock in my smartphone. So we're not talking about that level. We are talking about like when processes are happening a lot of times. Okay, like example that they were saying, you were trying to book a there is a like off in like flights. Okay, then you're like everyone rushing to buy things. And of course, you wanna. There are hundreds, like tens of thousands of people requesting for something. Or imagine there's a music festival and the tickets are sold like in 5 minutes. Of course, everyone like coming to do something, and there are a lot of requests. And you want to make sure that you're being fair and you're ordering everything right. Just an like a little bit dummy example I said, but you can look at it that way. So it's very important that preciseness. And then when we were talking about like Lamport clock, we say, okay, even if we are not that precise, it's fine. Anyway, that's the reality. We need to deal with it. So how we can deal with that fact? Let's use this happen before relationship between different events. Like this event A happened before B. I'm gonna ignore that little bit clock drift there on synchronization. As long as I say A happened before B, that's a fact I'm gonna stick with and I'm gonna follow.
Okay. Okay.
But I mean that's like.
Great.
I hope I answered the question.
Yes, you did. You did.
Okay.
Thank you very much.
No problem.
So, hello?
Yeah, we can hear you.
Okay, can I ask a question out of topic?
Okay, yeah. It's about drawing this picture or?
No. It is about like the assignments or projects. Like, how do you want us to upload that? Because I put it like in my own repo, but I don't know if you want us like to pull the other repository, create the folder with our ITESM ID and push create a pull request, or what's the way to push the repository?
I don't remember how I did it last. I'm awful at GitHub. I'm sorry about that. I'm gonna ask you something that it might sound dumb, but that's how I am about GitHub. I want you to have your repository in my account. How I did it last time? I don't remember really.
So to fork
This H, right? With a key.
Like no? I want to have them in my repository. Basically, I want them like to have all these different groups in. I can see them in my repository.
I don't know.
I'm going to tell you. But anyway, we are yet far from. Are we? When is the deadline?
In 2 weeks.
In 2 weeks. So I'll sort it out by next week. Okay.
Okay, yeah, because like for example, what I did is create a fork, and I have everything like on my own branch, but I don't know if you can see the forks. I'm also like not the best in GitHub.
That can be. I'll check it out for sure. Next week I come with an answer. Okay. Okay. Let's continue. Okay. Sorry, I'm going a little bit fast. I want you to have more time to rest again. Just something in parentheses, as they said, about the for you that are new and for the rest. We are groupings. I see still there are some groups here without. I mean, some students without grouping. So if you don't know, I'm gonna just randomly assign. Everyone fine with that?
Yeah, sure. Please do that.
Can you please, if you're here, turn on your camera? Let's continue. It's fine if you're eating, if you're drinking. I'm drinking constantly tea.
Yeah, I was eating, but
it's fine. I know the time is like dinner time. So so if you don't have any idea for the grouping, I can just assign. As it, everyone fine with that? Okay, I do that. And then for project, still there are people here. If you don't have any, again, idea, if you don't have idea, I can assign, then you can know who is you need to work with. Should we go like this?
I think we are missing all that part, right?
Yeah, for you three new, Pedro, Luis, and Charlie, you are not still in the system. I cannot see your name here. But when it appears, then maybe I just put you three in one group, okay?
Okay, what I was thinking is that maybe we can have a meeting another day with you and explain this because, for example, about the kit, I don't know what you're talking about what are the projects, all the same.
Yeah, again, because you're not here, because all these are included here. Okay, sure, we can have that meeting just with three of you, so I can explain again about everything.
Okay, thank you.
But if they just add you to the system, then you're gonna see everything here. It's already put. What I'm talking about is a project that we need to do.
Okay.
So if you have no idea, I just assign them. Everyone agree? Yeah.
Yes.
Sure. I'm just going like in order to fill up every groups. Okay. I'm like this. Just I mean it's random sort of. So this is Paul, Fernanda going here, Alejandra going here, and Pardo going here, and this one is full. That is full too. Group 7. So we have this. I'm gonna add them randomly. This is goes to group 1. I don't really even looking. Okay, I need to edit. So this one goes here. Edit. So please, I'm doing this because you need to know who are your group members and you need to work together. So if you, another thing, if you go to this section, you can see the people. I think you can even like click and email them through the system. Okay. Is it clear?
Yeah, I'm not able to see that there tab on my system. I can see everyone and presentation group, but I can get the project group tab.
So for presentation, again, I go like this as we did. I go like this. This is Paul. I go with. So I need to change this again. I'm gonna assign more people to the end groups, okay? Because again, we have 12 paper already I defined there, so I don't want to have more than 12 people. Oh, it's fine. So there are 3 new people. I'm gonna assign them like this.
Teacher.
Yes.
Regarding the project groups, I think Fernanda was supposed to be in the group number 6, I think.
Is that true?
Yeah,
yes. I mean, it's fine. I don't mind. I mean, like, if that's what you want to work, that's what I was asking you to do the grouping yourself. So if you want, I can do that. I'm sorry, group 2. She's moving.
Topics are still pending, right?
That's heartbreaking. So is it clear what we're doing here? Do you know your group members? Because, I mean, as Paul said, the deadline is coming in 2 weeks. If you haven't started, you are in deep problem, really. Unless you are doing it by your system, then you're gonna come up great out of it. So if there was any problem, let me know. And another thing I just came up with, later the next week, I put this grouping, I break out you to different rooms, okay? For like a 10 minutes maybe. I put you in different rooms based on your groups in the project so you can talk together. You can find out a way to communicate with each other, okay?
Okay.
So everything goes fine. I cannot do that now because it's gonna take time to do that manually, okay? Let's continue. For the new people, we're gonna set up time together, okay? I have your emails, take emails, so I'll contact you to set a meeting and talk about everything. So don't worry, okay?
Okay. But the deadline is the same? Is it still the same for us?
The deadline is same, but I think you can do that. There should have been problem. I mean, the thing is, what I see, maybe except Paul and his team, I think no one did anything so far. So you're in good shape. I mean, compared to others. I mean, you're all in troubles, but equally in trouble. So there's no problem with that.
Okay.
So let's continue and see how it goes. So what I'm going to talk, any questions about? Okay, what I'm going to talk now is about vector clocks and distributed snapshots. So we already talked about logical clocks. I'm going to mention some other things that I felt it's maybe a little confusing here. And also I'm going to talk about distributed global snapshots. So let's do a quick review on the Lamport clock. Remember again, the whole idea here is not to, because you want to know what's happening before what, and it's because it's important, okay? As they mentioned, like their example, which was really nice, you want to book a ticket, there is one seat left, there are 100 people are looking at that seat and trying to book. Of course, you want to know who is booking first, and you don't want that to be overbooked. You don't want all the 100 requests that comes at the same time, book the same, basically, seat, the last seat. So it's important to order them, and that's the idea with Lamport clock. Not purely, just purely like relying on the precise clock, like in a in a nanosecond, like difference between different process. So if, and they mentioned, if we show them by this, like if we show this with arrow, it is A happening before B, it means we can conclude Lamport clock A is smaller than Lamport clock B. And if Lamport clock A is smaller than Lamport clock B, or even B, even A, we don't conclude. I mean, we cannot conclude A happened before B because it can be the case, or the A and B can be concurrent. So we are using these for concurrency, not arrow with a line. Okay, correction. And when we are saying A and B are concurrent, again, we cannot conclude nothing about their Lamport clock. We just know like this is not the case. Another thing, Lamport clock timestamp do not capture causality, or let me make it more clear. They don't capture complete causality for all the events. You remember when they were talking about the Lamport clock? Lamport clock is this one. Okay, this is when you're talking about Lamport clock. They do not capture causality like this one. Okay, but look, this is concurrency, but I'm going to show it with example. And given two timestamps like CA and CZ, we want to know whether there's chain of events linking them. Another thing, one integer can order events in more than one process. You recall this when they were talking this? So you have this one, process 1, process 2, process 3. So you go start from 0. This is 1, 2. This is Lamport clock for this event, A in process 1. So you cannot order them like this, right? But what was this? This is what they talk, right? To consider the like a processor number and use that in order to order all the events. For example, when they have a equal like these two, like this one in process 1 and these events in process 2, that they both have the same Lamport clock, which is 3, how you can totally order them as he proposed, just look at the processor ID and give them the priority. Process 1 goes first, higher priority than process 2, okay? That's how we can have a total ordering. But still, this is slightly different with when we are talking about complete causality. Just remember that the Lamport clock does not consider complete causality of events. So a vector, so that's why we're going to talk about the vector clock. What is vector clock? Vector clock is a vector of integers, one entry for each process in the entire distributed system. So it's more or less like the same thing that we were doing with the total ordering, but slightly different. So you consider this, you have label events, label event E with a vector clock E. So you have all this is vector. I mean, we're talking about vector now, okay? So you have a vector with different elements. For each entry, CK is a count of event in process K that causes, that causally precede E. Confusing? Let's look at this picture. I'm going to go there. So initially, all vectors start from 0, of course. So we are talking about all. So we are talking about a vector of the numbers that you have this vector. If you have 3 processors, you have a vector of 3 elements. That is all 0. So you can see it more. Somehow you can recall that with that total ordering from Lamport. So we have 2 update rules when we are talking about vector clocks. For each local events on process I, increment local entry CI. For example, if it's process 1, you increment this one. If it's process 2, you increment the second one. If it's process N, you increment the N one, the last one, let's say. If process J received message with vector this, set each local entry C max CK DK. That's what I'm saying. It's more or less like what we were discussing there. But now we don't assign them just a ID of the processor. We are assigning the one vector that capturing all the processor's ID. So now you can see why I said Lamport clock can capture the complete causality when we're talking about distributed system, but vector clock can. It's much easier and simpler here. So we have 3 processors, process 1, process 2, process 3, and there are a set of events happening in each process. Again, when we are, again, something that I highlight here, when events are happening in one process, like process 1, A, B, C, I mean, whatever events happening here, they are happening in one process. So it's from the process point of view, it's much clear this process A happened before B because it's happening inside the processor itself. So process has not problem of the clocking, right? If everything happened in my system, of course I know which event happening first, which event happening second, because it's happening in one process. That's why these are, of course, this A happened before B because this is the physical time. Okay, remember, this is time is growing like this, increasing like this. So going back to the vector clock again. So we start from this vector 0, 0, 0, 3, 0 because we have 3 processes. So applying local update rules, so it start from process 1, the first event. So you start from 0, 0, so you increment this one. The first one, you go to the 1. It happened in the process 1 again, you increment it to 2. This is much more now like it makes sense and you can understand what's happening here. Then when it comes from these 2 processes that are messaging each other, basically C is reception of the B. That's why when it happens like this, the local vector clocks pgbacks on inter-process messages. We are talking about inter-process messages. This is intra-process messaging. So you know exactly what's happening here in one process. This is inter-process messages. So when it happened, then you send the vector clock, okay, because you piggyback that. So the process 2 going to receive that, and it's going to not going to touch this. You're going to just increase your own process ID. This is the first event in process 2. Is it clear? The second event in process 2. And then you piggyback this, and this is, okay, when it comes here, then here, you remember that equation that you consider the max value when it comes to this. So here, we have this process already. You get this 001, because this is happening here. There's no like messaging between these processes, between these events with E. So this is the first event in process 3 that get this vector clock. And when it comes to here, then this message arrives to F. F's put this 2, 2, 2, 2. 2 comes from this, right? It's very clear, right? So now you have all these vector clocks for all the events, and how you can compare them. Okay, I have all these vector clocks and how I can compare them. That's the question. So if vector clock A equal to vector clock B, it means even A is B for all K. So it means all of them are same. I mean, basically doesn't happen almost, okay? So if vector clock A is smaller than B, I mean, not if, vector clock A is smaller than vector clock B when even A is smaller or equal to B for all Ks, and vector clock A and B are not equal. Again, when I go to example, this make much more sense. Concurrency, when A and B are basically concurrent, as I said, we're showing with this, it means A is smaller than B and A is smaller than J. What it means, what I want to say here, basically we cannot compare two different vectors. Let's go back to the example that we were talking. So it's much clearer here. So in this example, vector A is smaller than vector clock Z. Then there is I mean, if you do this, if you show this, there is a chain of events connecting A to Z for sure. Okay. As you can see, vector clock A is smaller than vector clock Z. So it's you can see a chain of events. And okay, maybe I'm being confusing here. How you can compare these two? Because you can.
I have a question.
Go ahead.
Where is the vector A?
Yeah, same question.
Because I see the vector
That's supposed
Z.
to be basically W. I'm sorry.
Okay, got it. Thank you.
Yeah, sorry. This is W. Yeah, because there is no even A. This is W. Okay. Thank you pointing out that. So for this vector clock for even W is smaller than Z because there is these two numbers that you can compare them. Okay. Let's say that. For these events, A, okay, that was a mistake here. A and W, they are concurrent, okay? And it means there is no such chain of events between A and W. Basically, when you get this vector, okay, you look at this vector here, and then you compare it with this. Basically, you cannot compare them, okay? Because you have one here in the, like let's say location 1, then you have 0 here, then you have 1 here, then you have 0 here. There is no way you can compare them that which vector is smaller than the other one. So there is no chain of event between these two, as you can see on the graph too. So you remember when we're talking from the Lamport clock, saying like Lamport clock A is smaller than Lamport clock Z, you cannot basically conclude this. Like Z happened before A, you cannot even conclude A happening before Z. You cannot from this you don't get to like A happened before Z. You don't get this conclusion, okay? You cannot conclude this. Even you cannot conclude Z happening before A. What I'm saying? Sorry, let me correct. you can conclude Z is not happening before A for sure, okay? Forget everything I said. You cannot, from this, you can conclude Z not happening before A for sure, but you cannot conclude A happening before Z or A or Z are concurrent. So you don't know which one is correct from this.
Yeah, but then the example on the top is not right because that's.
This is the same. This is the same here.
Yeah. Okay. Got it.
I mean, you cannot for sure say A happening before Z. You cannot say that because it can be A happening before Z or it can be A and Z are concurrent. That's why you get this. But when we say vector clock A is smaller than vector clock Z, for sure there is A happening before Z, for sure. I mean, you see the difference. From, you remember when we were talking about Lamport clock, you say, like here, if you see this, okay, if you see this, you can conclude CA, like Lamport clock A is smaller than a Lamport clock B, like Z. From this, you can conclude this, but from this, you cannot conclude this the other way. But for vector clock, it's the other way. From vector clock A is smaller than Z, you can conclude A happening before Z, like the one that I show in the example. So vector clock timestamp precisely capturing happen before relationship and potential causality. So is there any question about vector clocks?
I have one question.
Go ahead.
Jace, in the example before, in that one, because event W and A cannot be compared, this means that those two are concurrent.
Right.
Okay.
Because there is no chain of events that connecting these two.
And I have a question for event A. Shouldn't the number 0 be 1 instead? Because
no.
whenever there is an
this is about process 1. Okay, this 0 here, this is process 1. This location is for process 2. Okay, because it's a vector. Okay.
Yes, but
and this is for process 3.
Mm-hmm. The vector clock starts at 0, 0, 0, but from the very beginning. But when an event happens, then okay, sorry.
This is the first event.
Sorry.
Right. This is the first event in process 2.
Mm-hmm.
Right.
Yeah.
That's why it's 1.
Right. Sorry.
This is the first event in process 1.
Yeah.
Go ahead, Pedro.
The causality can be in both ways. So, for example, if there is a chain between linking two events, then we can say that vector A is minor than vector C.
A and C. I don't see event C here.
No, what I'm saying is that, for example, if you have you don't know if the vector A is minor than vector C.
You mean if
okay,
VA,
but you know that there is a
if smaller than C?
Z.
Z, Z, this one.
Yeah, Z.
Okay, so this is smaller than this.
Now, what my question is the next one. You don't know. You already is an example. You don't know that vector A is minor than vector Z, but you know that they are linked. So we can after see that we can conclude that vector A is minor than vector Z.
I really don't get the questions, honestly. I mean, if I don't know their vector clock, that's you were asking, Pedro?
No, my question is that you have 2 points there, right?
Okay.
What about if we do the opposite announcement? Instead of you are saying if vector W is minor than vector Z, then there is a chain of event link by happens before between A and C.
Okay.
Right?
right?
But what about if we don't know about the vector, but we know that there is a chain of events linked by happened before between A and Z? Can we conclude that vector? Yeah, that one.
Yep. Yes. Yes.
In same for the second point.
For this one. Yes.
Yeah, for the second one, for concurrent.
Yeah, if I'm not mistaken, the other way works the same. If you know there is a chain of event between W and Z, you can conclude that vector Z is like bigger than vector W.
Okay.
That's the question. Yeah, it's just because that's problem we already like solved with Lamport clock. Because in Lamport clock, in Lamport clock, no, we cannot say the other way, right? That's a question. In Lamport clock what you were saying, you're saying if there is a chain of events between W and Z, if I say W happened before Z, right? That's your question.
No, a link of events.
Yeah, that's what we are referring with happened before.
Yeah.
When I say that W happened before Z, it means there is a link of event between them. I mean, in general, this is the same concept in Lamport clock. When we say A happened before B, it means there is a link of events. Here, like W happening before Z, these are the facts, okay? Like A happening before Y, these are what I know already. So it means there is a chain of events between A and Y, between W and Z, between A and B. Okay?
Call that transitive, right? Well, that's the transitive concept.
Yeah, that's the difference between Lamport clock and vector clock. Vector clock, I can consider the both. If I say vector clock, like for W, okay, smaller than vector clock for Z, I can conclude there is a chain of events. The same with seeing this. But in Lamport clock, it was not correct. In Lamport clock, seeing like Lamport, like if I put like this, I'm gonna put LC Lamport clock W is smaller than Lamport clock like Z. I cannot conclude anything from this.
Yeah.
Because they can be concurrent, or it can be W before happen before Z, but I don't know that.
Okay.
So
I have a question in terms of the comparison of the vectors.
okay.
Is there a possibility to insert another process, like process 4, in between the execution? Like, is there a way to insert another process, call it process 4, and then newer events would have a 4-dimension or 4 number or 4-digit vectors?
Yeah. It like n number. It doesn't matter. I mean, of course, for like when we're talking about distributed system, we are not just talking about 3 process, right? It can. It can
so
be.
What would happen? What would happen in the comparison? Like, you can compare between 2 events that the first one is 3-digit vector and the second one is a 4-digit vector.
You add totally one new process. I mean, this is going on, then you add one new process.
And the vector need to increase, right?
I mean, no, I think what he's asking, okay, you're working on this, then at this point of the time, okay, you decide to add another point, another process, right? At this point of the time. We're going to talk about that, that's totally different things, okay? I mean, not different, but we're going to talk about that. That's basically, I guess, like 7, 8, we're going to cover that. But that doesn't come basically to this one, it comes to another issues. If questions here, or what time is it? So let's talk about the distributed. Okay, the whole idea here was again talking about the difference between this logical time. Remember again, we are talking about logical time. Last time we talked about logical time, what we talked about was Lamport clock. That was another type of logical time. Today we talk about vector clock, which was more or less the same, but little bit, better in capturing complete causality, because you could capture better using vector clock comparing to Lamport clock. So now let's talk about distributed global snapshot. The one question that came, what happens if there is a failure, if there is something like that? That's what we want to cover here. So imagine this scenario, okay? You have a like landscape. Let's say this is your whatever. This is your distributed systems, okay? You cannot basically look at it all at the same times, okay? When we're talking about like snapshot algorithms, okay, you used to create consistent snapshots, or like what is the state of the distributed system that you have, okay, or the global state of the distributed system that you have. But this is not done like trivial problems because there is no shared memory between all the processes that you can look at the memory and you say, this is the state of my distributed system. And there's no shared memory, there's no shared disk. The one memory and one disk. So you can just capture this state and say that's the state of my distributed system. It's distributed, right? So like this flock of birds that you look at it and you want to capture it, and then you want to have it basically consistent. You don't want to have a bird here and then repeat the same bird here. You want to have a same consistent shot from all your perspective, let's say. So that's, you can consider it a distributed system. But it's not like, if you think about it, how we can do that. You remember the example I was saying about withdrawing money from the ATM, and at the same point, I mean, like maybe you're doing something with your phone, some transaction, your friend is transferring you the money that he borrowed you like 1 year ago and people forgot about it, and they're all happening at the same time, okay? It can happen, and it's happening every day. And so the system, let's say it's broke at the same time. And I'm not talking about like all the like distributed system of the banks is running on got broken. Let's say 2 or 3 of the servers for, I don't know, for earthquake, they just get out of the network. So what happens to the money, to the balance of your account? Did you receive the money that your friend was transferring? Did you, let's say you put your card, you press, and the ATM thought it's giving you the money, but the system suddenly, maybe the ATM is giving you money, still the database is not updated that you withdraw the money successfully. So the system is shut down, suddenly it's gonna come back. What's gonna happen to your balance, okay? Just an example to look at it. So it's, when we're talking about this state of the distributed system, it's not a trivial problem. It's a slightly complicated issue. If you have any idea how to solve that, you can share with us. If not, I can talk about the solution. How we can have a distributed global snapshots, or by snapshot, I mean like this. I want to capture the state of my system. I want to know what is the state of my system at any given time. For any failure that happens, I want to know what happened, right? So let's see how we can do that. So that's the idea. We want to know what is the state of the distributed system. You remember this example that we were talking. There is a bank in New York, another branch in San Francisco. You have 2 different accounts with this balance. So, of course, there is n processes in the systems with no. We are setting some like assumption here, okay, to simplify it first. Then later on, we're going to talk about all these failure issues. So, but for now, we are considering we have n processes in the system with no process failure. And we are talking about the processes, okay? So we want to know if there is no failure here for now. Let's say they're all working fine, but I want to have my state of the distributed system. I want to know at each given time, or the time that I want, what is the state of my distributed system. So again, consider there are 2 first in, first out. Okay, or first in, first out. Unidirectional channels between every process pairs, let's say P and Q. So between each 2 processes, or every process, we have 2 unidirectional FIFO channels, okay, first in, first out. So we call them PQ, channel PQ and channel QP. Don't get, I'm just setting The assumption later, I'm going to talk about them. But imagine the first thing, there is no process failure, okay? So the channel has the state 2, of course, the set of messages inside. And all messages sent on channel arrives intact, unduplicated, in order. So basically by setting this, these two, okay, these two, I already simplified a lot the problem, right? But it's much better to just talk like this, a simplified case to give you an idea. So we are imagining the message between this process P and Q, or between any two given processes, arrives intact, unduplicated, in order. If you remember the first week of the class that we were talking about network communication, like RPC, remote procedure calls, and we were talking about different methods of message delivery. So how basically can we get such pipe or people, I don't know how we call it, like first in, first out communication channel? That message can arrive intact, unduplicated, and in order. Anyone remember different type of message delivery from the first week we were talking?
One, it was like something like one. There are three different. I remember the word three different.
Okay.
The exactly ones.
Exactly
the
one.
Most ones.
At least once.
And at least once.
Yeah, at least one, at most once, exactly once,
Yeah.
right?
Mm-hmm.
So we were saying that the message arrives. Okay, so we are using at least once retransmission, because if you remember, at least once retransmission had the acknowledgement method that we do to acknowledgement from the message, and so we can use this method to make sure the message arrives. We say intact, of course, we didn't talk about it, but you can use network layer checksums in order to make sure the message is intact, didn't change the network. Then we are saying unduplicated. If you remember again, this was at least once, at most once has this deduplication schemes. That message could arrive more, but we could detect there's duplicated and we just ignore. And if message arrives in order, we can say like sender includes some sequence number to make sure the message arrives in basically in order. For the receiver can know this packet was even if they arrive at different times, that's what happens. At the receiver side, receivers can order them because they have a sequence number here. You don't need to worry about this. TCP providing a TCP protocol, providing all this basically functionality. That's why TCP is reliable. We use TCP. Okay. Just a review on what we were talking about. So again, I mentioned the global state is global state of your distributed systems. The first one is right. You remember again, we were talking about, it's the same thing I said, like it's, they mentioned also that when Fernando was talking, global distributed system is set up different processes, like physically located in different places, communicating through the network communication, or you can say via channels. So a global snapshot captures the local state of each process. Imagine that banking example, New York, San Francisco, two different locations. So the global snapshot captured the local state of each process, let's say program variables, and a state of each communication channel. So if you have a state of each process, I mean, if you capture a state of this process A, process B, and then also you make sure you're capturing the state of the channels, because there are, you remember we considered there is a unidirectional channels between these two processes. That means there are some messages or packets going from this process A to B, and some messages going from process B to A. I use a lot my hands, so sorry. And why do we need a snapshot? I already mentioned, right? That was one thing. Okay, you want to make sure it's against failure, okay, because you want to restart if the application fails. Then another thing is collecting garbage. You want to remove the objects that aren't referred. There are some objects in, I mean, you're using this massive number of systems. Of course, there are some objects at the end that they are not referred or they are not used. They're just using your system resources. You want to make sure that you get rid of those basically objects that are garbage basically in the system. And also you want to make sure you can detect the fogs. So distribute, basically a snapshot can help us with all these things. And what is the deadlocks is, for example, in this example, process A grabs and lock, like let's say resource A, B grabs and lock B, resource B, and then 8 for, like, let's say this event 2 to happens and B waits for event, and no one is going to release the first one, and that is what deadlock happens. It's like in sometimes in junctions, you can see that like this car is coming, this car is blocking this car is blocking that, and this car is blocking that. So there is deadlock there, and you just stop there. So by using a snapshot, you can make sure your system is can recover from the failure. Say the most important one that is happening a lot. You want to make sure you're collecting garbage. I mean, those objects that are not used or they are not referred to, you can remove that. And also there is no deadlock in the system. There's no like processor waiting for the other resources and like waiting there for a long time. So other debugging a little easier than work with printer. I don't know why I put that. It's like, for example, it's like you don't, yeah, sometimes happen. And you do that, and then you don't know why it's there and what I'm supposed to talk about there. It's like about basically debugging your operating, the distributed system, not just getting like output with printf, like dumping this, how to say, this log that is giant, and then looking at it, trying to debug the systems. That was what I'm supposed to say. Okay, so we're going to use this graphical example, which make it much easier to understand. So we have these two processes, process P, okay, process Q. We have two unidirectional channels between process P and Q. So let's call this channel PQ, which goes from P to Q, and channel QP, which goes from Q to P. So they are unidirectional. It's clear, and we have different events. Okay, you can look at, consider these are different events in different processes. So when you want to take a global snapshot, you want to make sure they are basically exactly one of each token. I mean, each token, let's say, representing processes, not processes, that's the events that happened there. For example, if this, let's say token B goes to P, you don't want to like get a snapshot here, then, okay, let me explain in the next slide. It's much easier. So we are talking here, we're talking about a consistent snapshot. Okay, you don't want inconsistency there, right? Inconsistency, like the example of banking, you want your balance to be consistent, right? You don't want to lose some money there in that example. That's a system failure happened. You want, of course, a consistent shot that is unique. Not it's same, you know, everywhere. If you get lost, just ask question, okay? Because I might lose track. I mean, what's happening here? If you get lost, just interrupt me and ask questions. So if we just get a snapshot from each process's perspective, okay, it can have problems. If we do justice, we say, okay, I have this, just do the snapshot here, okay, and a snapshot here, then you're fine to go. So I asked process P to get a snapshot, process Q, you get a snapshot, then I have the whole, like a global snapshot of my distributed system. If you just consider that, then that's going to be some inconsistency there. Why? Because of course the snapshot is happening independently on each process, And you can see here in this example what can be the issue. So P and Q put tokens in 2 channels and then take a snapshot. That can be one problems. We call it like disappearing tokens, let's say. So of course there are unidirectional channels that are communicating. Let's say like these 2 bank branch, New York, San Francisco, they're communicating, but there are some messages going on in the channel all the time. So they put the message in the channel or token, let's say in this one, in the channels, and then P take the snapshots and sees this, and Q take the snapshot and sees this. So you miss these tokens. Let's say this token was like reduced like $100 from this account. This was like pay 2% profit, and this was like add like $200 to the account. Okay. So you miss those comments, or let's say here, in this example, we're showing them by tokens. So you miss those. So you cannot just independently take a snapshot from each process perspective, because you're gonna miss the channels. It's clear? So another problem that can happen is like duplicated tokens. So P can take the snapshots here. You have these tokens, G and Y. Then you send the Y there, and Y is arrived to Q, and Q is taking the snapshot. Remember again, we are talking about independent snapshots, right? That's what we are talking about. Each process is taking snapshot. And again, talking about time inconsistency and all those things, this can happen. So then you have a basically duplicated Y token. You have Y token here and Y token here. Let's say this was like reduce, I don't know, like the task was like deduct $1,000 from this account. You deduct it once here in this process, and then you deduct it another times in this process. Just example, I mean, maybe I'm not being so careful with examples. So this, you cannot just do this. You need a better idea in order to do the global snapshots, because you need some sort of, like, you need also to make sure the state of the channels, and you cannot just do that so independently from the process perspectives. So what went wrong in there? We should have captured the state of the channel as well. So what we can do here, we can say like, define like marker message, okay, to track the state of the different processes and also the state of the channels. So this marker message, imagine this, I'm showing them with these graphical representations, distinct from other messages, this marker message, and channel diverse markers and other messages on a first in, first out respective, okay? Because we said already the channels are first in, first out. So what we're going to use is Chandy-Lamport algorithm. And again, yes, it's proposed by Lamport, and has funny story. Apparently they were, I think what I remember, I think last time I checked, like Lamport visit Chandy in like Texas Institute of Technology. There are two different people, okay, researchers. Visited there, then Chandy tells him about these issues, okay, about the total snapshot of they go out, they have dinner, they drink too much wine and they get drunk, and they go to their houses. So Lamport says when he is taking shower, he come up with the solutions. The day after, he goes to the Chandy, and when he presents the solution to Chandy, and he having the same solution. So basically, they come up with the same solution in 2 different places. That's why the solution called Chandy-Lamport algorithm. So we use these Chandy-Lamport algorithms for the global snapshot. So we'll designate one node, let's say in this example that we are using, node P or process P to start the snapshot. Without any steps in between, what P does in process P, records its local state, it takes snapshots, and then it sends a marker on each outbound channel. So nodes remember whether they have snapshotted. So if the process P takes the snapshot, it remembers the snapshot. On receiving a marker, a non-snapshotted node performs a step 1 and 2 here. So what is happening, I mean, in plain English, it's a plain English here, it's a little bit more plain English. It's process P start, take a snapshot, send the markers in the outgoing channels. I need to remember I already have the snapshot. So when this marker arrives to process the other process, let's say Q in this our example, the process to record its local states and then send the marker back to the process P. Look at it here. So P snapshots, okay? P take the snapshot, record the state of its local systems, then send the marker in the outgoing channels, and let's say send another process. You remember last time it was the duplication issues in this example. So this is the send rule. Send marker on all outgoing channels that we discussed. So immediately after taking a snapshot, send the markers. So sending the marker happens immediately after sending a snapshot before any other messages. So you take the snapshot, you send the marker first, then you do the other, like further message, like say Y here, token Y. So receiving process on the Q side, let's say Q here sends token O, or let's say this event's happening. This message is going to from process Q to the process P, from New York to San Francisco, okay? You remember last time we had this problem with missing tokens? So we have this snapshot here. So Q sends this token. Let's say Q receives marker, this one. Again, remember they are first in, first out. So marker came in first, so of course it's going to out first. Process Q received the marker. So when you receive the marker, this is the rule. If you are not snapshotted, you take the snapshot. So Q take the snapshot of the state of the system. So this is the state of the Q. And on receiving marker on channel C, record C state as an empty. So if you receive this marker on this channel, okay, you consider this state of the channel as empty because you receive the marker here. So you remember the receiving rule. You receive the marker, you take the snapshot, you consider this channel empty because you receive this marker from this channel. Here, don't get confused. I'm talking about two process PQ. It can be another process Y here, okay? And there is, again, two different channels here. That's why I'm saying from the receiving channels, okay? So when it happened, you record this as an empty. Then Q send marker to P. So after you do this, you remember the snapshot rules? When you do the snapshot, send the marker. So Q does the snapshots, send the, does the snapshot, send the markers, record this channel as empty. Okay. So Q send the marker, P receives the orange token. It's orange, it's supposed to be orange, okay? It's green here, okay, don't confuse. It received this token and then the marker. Okay, you receive this because this is again first in, first out. This is going to go first, then this is going to follow. So receive the token and receive the markers. And another receive rules, if you already snapshotted, okay, because you remember the P had initiated the snapshot. So if you are snapshotted and on receiving marker on C, record C state, all message from C since snapshot. What it means, again, in a little bit more plainer English, it means if you receive this token here and you already have this snapshot, okay, you're going to record the state of the channel as everything that you received from this channel before the token. And in this example, the process P received O before receiving the token. That's why record the state of the channel as O. So now what's happened, if I remove all this mess, you have the state of the P, you have another snapshot here, you have the state of the channel for QP, and you have the state of the channel for PQ. And if you put them up together, you get the complete picture of the distributed system. It's very straightforward, really. There's no complication here. To P start, I'm going to do it fast again. You remember P start, take the snapshot. As soon as you did the snapshot, you send the marker, the Y is going. I mean, of course, things are happening there. Q is going to send one event, and meanwhile is receiving this marker. When it receives the marker, does the snapshot. As soon as you receive the marker, you take the snapshot and you consider this channel that you received the marker. Because, okay, another thing to clarify here. When you receive the marker, you take the snapshot because you did not take the snapshot before. You receive the marker, you don't have a snapshot yet. You take the snapshot, okay? Then you record this state of the channel that you received this marker as empty. Then this is because you did the snapshot, so the rule is telling after you did the snapshot, send the marker quickly. So you send the marker. Then after you send the marker, this message arrives in P. First, this is going to arrive, then the marker is going to arrive. So when P receives the marker, it looks, based on the receiving rules, if you look at its snapshot. Did I already snapshot? Yes. So what I'm supposed to do, I'm supposed to consider the state of the channel, any message that I received before this token. So the state of channel is going to be this. So now you have everything here without any duplication, without any missing tokens. And how you know these events are happening? By vector clocks, okay? You can already order every event, right? So there is no problem of ordering these two events here. Did I receive O first, or did I receive the token? Did I receive token O, or did I receive the marker message? Okay, that's not issue anymore because you can order them. So you order them, you know, you receive this O first, then you receive the token, you have already a snapshot, you record this state as this one because you just received it. Questions? No?
Yeah, I have a question.
Go ahead.
When the process P starts the snapshot, in that moment, it had to have something like a buffer to storage the channel QP, or how it will know that it have to storage, for example, that there is a message sending from Q to P.
So you mean like in this stage, when the P starts snapshot beginning, or here?
Yeah,
or here?
Yeah. When P starts, when P creates the snapshots, the marker is sending through the channel PQ to Q. Q receives the marker, and Q sends the marker again to P. But at the end, according to the Chandy-Lamport algorithm, at the end we need to storage the message from the channel QP.
Yes. Okay.
Yep.
So
yeah. So when the snapshot starts in process P, do we start to buffer or to storage the message that are traveling from Q to P? Because at the end we need to storage that state, the message that are traveling between Q and P.
Yeah, the messages that are here, you mean a storage for channel or a storage for the process?
For the channel.
I mean by the channel, consider it the network connection between two different processes.
Yeah.
That's what I mean channel. This is
but
okay.
Okay. Maybe I cannot explain myself very well.
No, I understand. For example, what if you mean, let's say, what if this channel is like this network connection is disconnected, right? What happens to the state of this channel?
Not exactly. When the snapshot starts in process P,
okay,
in that moment, do we have to have a list, let's say a listener or buffer or something for the channel QP?
No. At the beginning, you don't need to, okay? At the beginning, we say we designate one node, no matter what, P, Q, doesn't matter which one, to start the snapshot. If you have thousands of nodes there, assign one of them to take the snapshot. Doesn't matter which one. And you don't, at this point, so here, let's say this in this scenario, we have just two processes. You start the snapshot. So you record this state, you don't, when you start it here, you just start it, okay? So process P, we say process P start. Start taking the snapshot. So I take the snapshot, right? Then I set the marker. I don't need to record any state of the channel. No matter if there are packets here, I mean, doesn't matter. I don't need to record this.
Is the marker part of the snapshot?
The
marker is a message.
Marker is a message, right? So basically, the idea is you take the snapshot, you send the marker. You don't need to do anything for now. You don't need to do anything with the channels, right? That the sending process is simple. When you take the snapshot, send the marker. That's it. That's all. That's all the rules for sending process. You take the snapshot, send the marker.
Okay.
When you receive it, of course, there are other things happening. I mean, there are two different systems that are communicating, right? Another message, another update. Here we are showing it by token. So the receiving, and okay, the send, okay, I said that when you send the token on all the outgoing. If there are another process here, you send this token to that process as well on all the outgoing channels. So you take the snapshot, you send the tokens, but the receiving process is a little bit more complicated here. When you receive, okay, of course, there are, again, things happening here. I mean, Q is not waiting for the marker. Things are going on, right? So when you receive the marker, so the receiving rule tells when you receive the marker, take the snapshot. Take the snapshot, this is happening first, okay? And then, I mean, let's take the snapshot, record the state of the channel as empty. So no matter what is in this channel, you consider it empty. You don't.
Yeah, we don't care about the channel because we already have captured Y in the snapshot, in the previous,
I mean,
right?
Yeah, at the end, everything's going to work, right? But, I mean, but for process Q, I mean, doesn't know. For Chandy Lamport, that they come up with the whole algorithm, they know at the end, everything is going to be consistent. So process Q, according to the rule, says, okay, that's my rule. Receive the token, take the snapshot, consider it empty. And again, the sending rules, take the snapshot, send the token, right? So the Q sends back the token on the outgoing channel. The token goes back. There are, of course, other things. Again, when the P receives the token, when this arrives, nothing happens yet. Okay? I mean, there's no snapshot. But when this arrives, okay, then when this arrives, then process P, according to the rules, considers the event of considers the state of the channel that received the token because it already have the snapshot. If you don't have the snapshot, you take the snapshot. If you have the snapshot, you consider all these messages that you received before token as a state of the channel.
Yeah, and that is exactly the question. How the marker knows that something comes before
The marker doesn't know. The process P doesn't. It's like it's a system.
Yeah,
You're talking about distributed system, right?
Yeah, I have another question, but is how the channel is captured before anyone's know that something that it needs to be captured.
You don't
because for example, P take the snapshot, sends the marker, Q receive the marker, take the snapshot, but then when Q sends the marker, the token, the O token arrives to P first than the marker, right?
O arrives before marker, right?
Yeah. So then, when P is going to take the capture of the channel?
P doesn't capture the channel actually because we are not aware what's happening inside the channel, right?
Yeah. So
because I mean the message going on maybe at this time, okay, when I receive this, P is already here. I don't know. I have no idea what's happening inside the channel.
Yeah.
But I just follow the algorithms. When I receive this token, okay, I have already snapshot. So when I receive token, I see, okay, I already have the snapshot. So there is this rules, okay? If you already have the snapshot, so you say, I'm receiving the marker on the C, channel C, you record C's state. All message from, so you record C states, of course you are not aware of the C, okay? But what you can consider as the state of the C or as the state of the channel, all the messages from C since snapshot. So you take the snapshot here, right? Which process P received the marker, and now look at the messaging that it has, right? After the snapshot, since the snapshot, since he did this, okay? Okay, let me tell you another example to make it more clear. So my point is, let's say even there is like a K here, okay, that arrives before O, okay? So this arrives first, this arrives second, this arrives third. So process P, according to the rules, receive the markers, and then it says it looks at its snapshot and say, okay, after I did this snapshot, what messages I received? I received K and I received O. So this state of this channel, I'm going to consider K and O.
KO.
Yeah, that was purpose.
Hey, this is still considering that we are in a perfect, beautiful environment where everything is.
Yeah, that the messages are not lost, the process is not terminated, it's not dying, everything arrives.
Great, because I believe that in the real life example, the marker can be sent at the same time as, I don't know, another event. Let's say the marker is sent at the same time that the token O is sent. Yeah, well, yeah, whatever. I think you'll explain in future lessons.
The only thing we're considering here, I mean, doesn't really matter about what's happening inside the channel. After the class, do any scenario that you can think of, the most complicated scenario of everything going on back and forth, just consider these rules. You're going to end up with a consistent shot. You're going to end up with a perfect shot without duplication, without missing tokens.
Yeah, actually, this is the worst scenario, right?
I mean, yeah, I try to make it complicated, that there are messages here. It's not just token. There is this message that pass through without even receiving anything. Anything you consider, you're gonna end up with a perfect snapshot.
Yeah. Okay, got it.
Question.
Okay, go ahead.
If a reset happens right after this, token Y is gonna stay on P, right?
Which one?
Token Y.
Okay. After this, you mean why the Y didn't arrive?
No, I mean, if there's a reset after this, what happens with token Y?
Okay, that's the thing. That's why I mean I was trying to avoid these questions by setting up this RRV.
The perfect environment.
By this, sorry, by this, okay. I say there is no failure. Because if you consider failure,
It's gonna be on P, right? Yeah.
If you consider failure, then the whole story, I mean, actually, that's how we're following. Then later weeks, we're going to talk about what happens now if they fail. Okay. So we're following, like we're simplifying it, we're explaining it, so you have this idea. Then we're going to make it more complicated. So what happens if they fail? If some process fails, I mean, what's gonna happen to the consensus about the state of the system? When one process dies, another process added, like the question was like, what if you add a process? Of course, you want to scale a distributed system. Another benefits of distributed system is it's scalable. So it's not that you have 10 servers and that's it. You're just bound to 10 servers. Of course, that's when I scale. Your company is growing. You're going to go to 10 to 100 to 10,000, 100,000 of different servers in different part of the board, right? So it's scaling. So what's happened in those scenarios? So we're going to cover all those things, but in later classes about, I mean, there are more complex algorithms going to come up. Questions about this? More? No? Sorry, go ahead.
Well, I associate it like this. P contains the elements J and G. So I sent like a copy of J to Q, and Q is doing some process, and it says, well, when you send me Y, I give you O, for example. So it gives me O and my element Y again. So it keeps like this.
You mean before like this O goes, Q needs to receive Y?
Yeah, it could be a case.
Yeah, I mean, I cannot do really all the possible scenarios here, but you can imagine. Okay, there is no, let's say there is no O here. Okay, O is not here. Just imagine that scenario. O is not here. O is here. Okay.
Okay.
So you receive the marker. You take the snapshot, right?
Yes.
And you're waiting. You need this Y. That's an imaginary situation. You're waiting for this Y, right? So you receive the marker. The marker arrives here. It's a nice marker. You take the snapshot. Now you have the R, P, B. Sorry for the bad writing, and O, right? You receive the snapshot. You receive the marker. You take the snapshot. You send the marker, right?
Right.
Okay, it's fine. This is not here, okay? The marker comes here via, I mean, when you receive, you remember again? When you receive, you say the state of this channel is empty. So you get this, you send this marker, there is no O here. Marker comes, marker arrives here, right? So P receiving the marker, and look at this, it has already a snapshot. So what other messages P received after this snapshot? Nothing. So the state of the channel is empty.
Okay.
Now you have all the token. There is no missing token. You have G, Y, R, P, B, O. There is no missing token.
Okay, I got it.
So I said, I mean, you can consider any scenario, just follow the rules of the sending and receiving. You're gonna end up having the perfect snapshot.
Okay.
How you terminate the snapshot, how you make sure you're done. I mean, we are talking about two processes, right? Distributed system is a lot of different processes, okay? So who is going to decide, okay, we're done with taking snapshot, I'm ready. No one process decides when it terminates, okay? Eventually, all processes have received a marker. I mean, even you consider 10 different processes, their marker is going back and forth between the network. Eventually, all of them are receiving this marker. Of course, there are cases, network messages corrupted, network failure, process failure. We're going to cover about those inconsistency later. Eventually, all processes have received a marker. All processes have received a marker of all the n-1 incoming channels. If you have 10 process, you have received all the markers from all these 9 incoming channels. Later, a central server can gather the local state to build a global snapshot. When you receive all these things, the marker, all the processes receive the marker, and from all the incoming channels, basically a centralized server gather all these different snapshots and make the global snapshot. Like the picture that I show you from the flocks of birds, you can take all those captures, you put them together, a central server, and sees the whole picture. Just before we finish, I'm sorry I didn't give you a break because we are almost there. So I'm going to talk about the Candy-Lamport reasoning about it and talk about consistent talk. So global state is the n tuple of local states. You have n different systems. Of course, the global state is n tuple of local state. You have all these n different snapshots. You want to put them together. A cut is a subset of the global history that contains an initial prefix of each local state. So we have this. I already talked about the global state. You put everything together and you get the stage of the system, distributed system. And what is a cut? Cut is a subset of the global history. Okay, that's it. It's very simple. So therefore, every cut is a natural global state, of course, because you're taking a cut. I'm going to show you. And intuitively, a cut partition the space-time diagram along the time axis. So if you have this time processing, you get the cut of the snapshot. So you have all this history of the events that happening, right? So you cut, it's like a cut, taking this cut from the state of my system. For example, I can take a snapshot of all your pictures here, faces here. That's a cut of the state of the system that you are at the moment, that you're all tired. So we can have two different cuts. We can have inconsistent cut versus consistent cut. When we're talking about Candy-Lamport algorithm, it always generates consistent cut. And what consistent cut means, a consistent cut is a cut that respects causality of events. So we already know what is causality, so we shouldn't be having problem with this. So a cut is consistent when each pair of the events E and F, if F is in the cut and E is happening before F, then even E also is in the cut. Complicated, just look at here. So we have all these events. We have even A, this is like even B, even F here, even E here. These are events, okay? All these are events. So you want to take a cut, okay? So this is a consistent cut. So basically, I take a snapshot of system here. This is my global state, right? This is my global state of my system, not including this text, just this part. A cut is like history of the system. So I take a cut and I look back. I have all this history. And this is a consistent cut because E is here and B happened before E. So B is here, A happened before B, so A here. And H didn't happen before anything, so H is here. So this is a consistent cut. This is an inconsistent cut. Why is inconsistent cut? Looking at this, this is the time progress. Okay, this is the time. Time is developing. Why this is inconsistent? Because D is in my history, okay? and G happened before D, and G is not in my code. Is it clear? So this code is not allowed by Chandy-Lamport, because Chandy-Lamport is always returning a consistent code. And it's important to return consistent code because you cannot just see why I have the extra $1,000 in my account without knowing what happened. I want to know my friend transferred that $1,000 to me in my history. If I want to take that shot, I want to know this happened. My friend transferred me 1,000. That's why I have $1,000 in my account. So that's why, I mean, having consistent code, it's helpful. I mean, having it inconsistent is not going to help us much, because you're going to see, okay, I'm going to look at the history of my distributed system. I'm going to look at this code, and oh, there is a $1,000 extra money in this account, and I don't know why it's appeared there. I have no idea. But if you get it consistent, okay, if you make it consistent, either you make this one consistent, you remove this, okay, or you remove this is a consistent, or you put that included, then you make the consistent code. So takeaway points. Vector clocks precisely capture happen before relationships. Distributed global snapshot, we already have this, we considered FIFO channel, first in, first out channels. Of course, we can do that, and we know how we can do that. TCP, right? For all those requirements that I said. Intact, what was that? Arrive intact in order, I forgot.
Unduplicated.
Pardon?
Unduplicated.
Unduplicated, right? Yeah, intact, unduplicated, and in order. And so we talked about Chandy-Lamport, which take the global snapshot and also provide us with consistent code. And it used the marker message to coordinate and make sure we get a perfect shot. And Chandy-Lamport provides a consistent code, as I mentioned. Any questions about what I just talked?
Can you explain again the code?
The code is, we were talking about the code is like basically a history of the my global system. This is my I mean, when I'm talking about global state of my distributed system, of course, they are all in my global state. Let me show you. This is my global state, right? There are even up to these events that happening here. This is all my state, my global state of my distributed system. But I want to like cut, let's say, the history. I want to separate this history of my distributed system. Basically, like take a snapshot, but basically you can consider this cut like a subset of the global states. This is a subset of the global state. Then this is, I'm not going to talk about that later. So this is a cut. Basically, you taking this snapshot from here or this cut from here and all the way back, right? So this is your history of your distributed system so far up to this point that you take this cut.
Okay.
Up to this point in time. Let's say up to August 26, 2020, 9.9. This is the state of my system. Okay.
Okay.
9 p.m., 9 hours. So of course, this is going on. Things are happening now. It's 9:10. Events are happening. So this is the consistent cut. So for cut, we can have consistent and consistent. So the idea was if this is in the cut, okay, or no, not this one. If E is in my cut and B happened before E, right? You remember this? B
Yes.
happened before E. So if this is the case and E is here in my cut, B should be here for sure to have a consistent cut.
Okay.
Here, for example, in this example, D is in my cut, and my cut is like all this space, okay? all this space I'm highlighting. This is my cut. My cut is all this part. Okay?
Okay.
From this line to the past, this is the time is developing like this, right? So in this one is inconsistent because even D is here and even G happened before D. But G is not in my my code, so it's inconsistent code. So you cannot return this code by Chandy-Lamport algorithms. So
Okay,
you need to provide a consistent code. Or this one, or this one, or at this point of time, let's say you are taking codes. This is your consistent code. Okay, where you're taking the code at this time. Let's say. Again, I mean, why? Like it's not like a straight line. And why is not? Why I draw like this? Not a straight line like this. And this is not straight, but consider it straight. Because again, the capturing are happening like independently. This is capturing, this is capturing, this is capturing, right? And the timing are the time skew, right? The time drift between the different events. Maybe at this time that we started the snapshot, this is like 3 milliseconds earlier than this process, and this process is like 4 milliseconds behind this process, the time in that local process.
Okay.
That's just an idea. I mean, again, going back to the time example. So if you're taking this code, this is the code, and this is the consistent code. More question?
What are cuts useful for, or why do we need cuts? Like the history.
Why do we need cut? Because you want to have the state of your distributed system.
Okay.
I mean, of course, I'm looking at the global state, but at some point I want to have this. Okay, let me tell you this one. And you never back up your system? Maybe
No.
maybe you don't. If you don't, do it, please, for sure. Before ending this week, back up your system. That backup is like a shot, right? Like a snap, like a cut from the state of your computer. Of course, it's changing. There are new files generating. You're generating new file coming, downloading files. But that backup that you're taking is like a snapshot of the state till that moment in time. You have that.
Okay, yeah, makes sense.
Are inconsistent cuts useful for that matter?
I can't think any reason that it can be useful, honestly. Because if you're looking back at it, then a lot of problem can arise by looking at an inconsistent cut. Because you see events that happened and you don't know why it's there, you know? Like the best example I can think is like the bank account information. For example, if you have this as a history, and one day they're gonna check the bank and they're gonna see like $1,000 just in the one account without any sender, without anything. I mean, most probably they're gonna, I mean, when they audit your account, they're gonna put, I mean, that bank is gonna be in problem where this money suddenly appears here.
But at least I think you, from an inconsistent cut, you can create a consistent one, right?
Which one?
From an inconsistent cut, probably you can create a consistent one.
If
like for example, in this case, if I just get rid of the D event, then I would make it a consistent cut.
Yeah,
and
that's the thing.
Between those cuts, you would lose less.
Yeah, okay, you want to take this and you end up with this. Of course, if you have this and you know this is happening, you already know, let's say in your system, that G happens before D. So of course, either you have to remove G or, I mean, remove D or include G somehow to make it consistent. That's why I said, like, talking about Chandy-Lamport, this has never happened. I'm not aware if there are any other algorithms that they generate inconsistent code for any possible reason. No idea. But I don't know. I cannot really think of any possible reason that can be useful unless, let's say, you're taking the shot and this process at this time that you're taking this shot, maybe this process is died for any possible reason, and you have this D and you have this, and you know a process is dead. And anyway, you want to take this shot, okay? And later you want to think about a way to recover from that inconsistency. By when, I mean, that's what we're going to talk, not about this inconsistent code, but when a process fails, come back lives, what's going to happen to the state of the system? What is the latest state of the system? Or how this process can get updated with the latest changes. Questions? No? I think you're just too tired. Okay, just let me go. I come up next week with the question. It's fine. I'm done. Oh, yeah, I'm done. I mean, I wanted to talk about something else, but there's no time. I'll talk about that later. I mean, that was extra. You know, the takeaway point is the last slide. That was some extra, but I cover it during next week. No question? If there is no question, thank you guys. And have a nice evening. And just let me stop sharing, stop recording.